It's in the same force from the opposite, the different direction.
Okay?
Same force from the different direction.
And you're
So,
still, I'm not disagreeing with zero. I'm good with that, but you're missing something. No,
I have.
still missing something.
Negative.
Thank you, units. Don't forget units. You can make it 0 newtons I hat also. So negative 0 newtons I hat also works, or just 0 newtons. And you put a little vector symbol over the 0, because, there's no force, so it's whatever direction you want. All these would be acceptable answers here. This situation here is known as equilibrium. If the total force acting on an object is 0, the object is in equilibrium. Or, since force and acceleration go hand in hand, as will be definitely talked about later, acceleration is also 0. So the total force is 0, acceleration is 0, and vice versa. I mean, if one's true, the other one's true. And if acceleration is 0, there's no change in velocity. Now, these two things we'll get into more detail in chapter 3. Unfortunately, in physics, there's about 4 different concepts. It'd be really great if we all teach simultaneously, and then we can start building from there, but we have to start somewhere. So acceleration and velocity are terms that we have not really talked about in any detail. But the important thing here, well, I guess I do need to talk about velocity just a little bit. This is velocity. How fast an object moves. And in what direction.
Is that a G?
Where, here? That's an S.
That's an S.
Yeah, this is newtons, meters per second squared, and meters per second. Here, I'm sorry. I should have listened. Questions about this definition of velocity? All right. So if velocity changes, so if there's a change in velocity, if the change in velocity is not 0, so this delta right here just means change. So if the change in velocity is not 0, in other words, there is a change in velocity, then there exists, backwards E there means there exists, acceleration which is not equal to 0. So if the velocity changes, there's acceleration. That's what I'm going for. Non-zero acceleration.
What is the units on the acceleration?
Meters per second squared. And I do recognize I've just used some vocabulary words that are officially new to you. Just a little bit of an illustration for acceleration. I assume everyone in here has driven or at least seen someone drive. As you drive, there are 3 things that a physicist would call an accelerator that you have easy access to. What are the 3 things that you have in a car which could be considered accelerators? One.
Gasoline.
I hope you don't have easy access to gas simulator, right?
Oh, easy access, oh, I see.
So gas pedal's one.
There's an actual accelerator, right?
Well, that's generally in the car, what people call the accelerator is the gas pedal, but there's actually two other things that you have access to that would also be accelerators from a physics point of view.
Gears?
Pardon?
Gears, the gears?
Don't have easy access to the gears. I'm thinking about things that you can physically touch. And let's just make it automatic transmission. I don't want to deal with the clutch right now.
The steering wheel. Steering wheel?
Yep, there's the second one. Because what does the steering wheel cause the car to do?
Direction.
Yes. Direction changes, velocity changes. There's acceleration. And the third thing?
Right?
Yes. Speed up, slow down, change direction. Those are the three things that cause acceleration. So if the total force is 0, there's no acceleration, which means speed does not change, direction does not change. So this object right here, total force is 0. So what is the acceleration? All right. How fast is it going? So you said staying still?
Mm-hmm.
So what?
Yeah, it's not moving.
Why do you assume it's not moving?
We can't see it move. Because if the acceleration is 0, then the velocity.
No.
No?
Change in velocity is 0. This is the point of this. Equilibrium says nothing about how fast an object's moving. Let's look at it a different way. How fast is Joanna moving right now? That's Joanna right there. I assume you can see her. How fast is she moving?
She's not.
Pardon?
She's not.
She's not moving? What about now? How fast is she moving? She's coming right at me. She's not stopping. Stop it! Am I correct in saying that she was moving towards me? I heard one yes, and then something over here.
Yes.
You guess? Okay. Cheyenne, you agree with the I guess? Was that your?
I don't know, I'm not sure.
All right, let's take the eraser. The eraser, instead of picking on Joanna. An eraser here, relative to us, is not moving. Somebody make an argument that it is moving.
Say that it's moving at the same speed as the Earth?
There you go. So when you're talking about velocity or speed, it's always relative to something. If the police car is following you and he pulls on the radar gun, you're going the same speed. If he pulls out the radar gun, should register as 0. If you're going the exact same speed.
Ooh, I should say that.
Or in one case, if you're in Casey, South Carolina, don't speed. A friend was pulled over, a fellow graduate student got pulled over. The policeman said, I was doing 45 in a 35 zone and you were right behind me, so you were speeding. Got off with a warning. All right. So equilibrium only means that the velocity is not changing, which means that whatever its speed is, it's going to stay the same. Whatever its direction it's moving, it's going to stay the same direction. There's matter of fact, we can break equilibrium around. We can break equilibrium down into static equilibrium. This static equilibrium means the velocity is 0. That's relative to the observer. So as I was walking towards Joanna, or as Joanna was hovering towards me, you're claiming that she's not moving, or my claiming she is moving, are both correct. Velocity is always relative to something. So static equilibrium means not moving relative to who's ever doing the observing. Usually we assume the Earth isn't moving for a lot of what we do, but it doesn't have to be. And the other one is called dynamic equilibrium. And this just means that the velocity is not zero. In other words, it's moving. And just a quick flip back, the steering wheel, which the second thing was said, usually it's the third thing said. I appreciate that it was said second. All right, questions to hear? This is supposed to be a beam, just a board, something. Make it look more like something. Let's make it a 50-kilogram board. And it's being held up by two strings here. And then the person standing here, the mass of 100 kilograms. So I have this large beam right here. The person standing at this spot has a mass of 100 kilograms. The beam itself has a mass of 50 kilograms. I have two ropes holding it up. The tension in the rope on the left is 600 newtons. What is the tension on the rope on the right? For better or for worse, I'm introducing two things here. One, how do you find a force if you have the mass? And two, we'll employ this equilibrium idea.
So he's not standing in the middle, he's on the right side?
Right. He is not smack dab in the middle. And beam is in equilibrium. Static equilibrium or dynamic equilibrium, it does not matter. So if you picture window washers and got that giant scaffolding moving up and down, or it's sitting still, but the velocity is not changing, whatever it happens to be. So, force diagram. I got beam. I went ahead and we got this tension over here, which is called tension left, which is 600 newtons. Tension right. I have a person. All right. All right, so tension's already taken care of. Technically, there's a rope there, and there's tension pulling down on the rope, but the rope's attached to something, but we just simplified it. So tension is taken care of, there is no other.
Weight of the person downward, weight on person downward.
Thank you. So I got weight of person, and then there's presumably a planet down here, weight of person. And yes. Now, we will assume that it is a uniform beam. And what that means is that we assume that the weight, it's as if the weight is acting at the very center of it. So I have weight of beam in the center, although it doesn't matter for the problem that I'm given here. All right, weight done.
Normal force.
down on the person.
Down on the person?
Oh no, I'm down on the beam.
Down on the beam. All right, so I got this normal force down here.
Up on the person.
Okay. And I didn't state this, I thought it in my head intensely. Person and beam are in equilibrium. The person's not jumping on the beam, the person's just standing there. It is sadly time to go. So we'll leave it as a cliffhanger for Wednesday. And I probably should make a note that this is where we left off. That'll be enough. So long farewell, we'll do the same good.
Thank you.
I have a couple questions about the narrow.
Yes.
Just like when you send all the decimal places, it needs to go to the same number. So, like in the data charts, all of those numbers, like the average number and the first recorded numbers, all of those need to go to the same point.
Because those were all, you had only whole numbers written down, right?
Yeah, whole numbers for the first ones, and then some of the averages, it went to like the tens place, so I didn't know if that meant all the whole
Either,
numbers.
if you round off to the nearest whole number, I'm fine with that, or if you wanna take it out. If you care about significant figures, then it would definitely, the averages should be whole numbers.
Okay.
But if, I'm not concerned about significant figures in 110. Matter of fact, I barely care about them in other courses. So, either way you wanna do it.
Okay.
Whatever you do, just please be consistent.
Okay, so I think I'll just leave it then as it's whatever number and then point just one extra digit.
Okay.
In all of the averages.
Okay.
And then for the ones that came out as a whole number, I can add a 0.0 on those ones. For
Okay,
the
I'm
average.
fine with that.
Okay, and then the one other thing, for the percent error, you had formatted it like the symbol percent and then error. So for the number, should I not put another percent sign afterwards?
Because I do not have percent, the percent symbol in parentheses, you do need to add it at the end of the number.
Okay.
And I don't know why I do that, but I'm consistent throughout the course where I do not put the percent symbol in parentheses.
Okay, sounds good. Thank you.
Yep.